Okay, my friends, Roger once again, about to blow your mind. Neutrinos, the biggest thing in science now, in physics, is neutrinos, ghost particles. Guess what? They can interact with light after all. Well, guess what? They are light. Okay, so they're looking for the tiniest particles in the world, and they're trying to use heavy ion collisions at Atlas, which is the CERN people. And they're trying to smash these things to get these little bitty particles to give off. And they're having a live discussion about it. I missed it, but I left a comment, and I'm basically the only one that did. Somebody else said they hated to miss it. So I said, hello, my friends, I would like your opinion on this YouTube that I put up about my standard model, well, my model, which is not like the standard model. They say I say the standard model needs slight changes. Take a look at this, please. Shows clearly light is made of dipoles. That is what light is made of, dipoles. And it's dipole electron flood theory, and then I go on to say about the number of particles and so forth. The heavy ions are from extra dipoles, and light ions are simply lacking the full number for stability. It's not that hard. Now let me show you the actual research and actual experiments that show this. Now don't forget, the only reason they're doing this stuff is so they can find the smallest particles that exist. They want to know what protons are made out of, and nobody does. So they're using heavy ions to get little bits and pieces to bang off of there and see what they are. Now, this is Dr. Martin Rybar, works as a research scientist. He has been a member of Atlas Collaboration since 2009. He's getting groups together to study this stuff, and he tries to understand our universe at the most fundamental level. He enjoys communicating science. Now, I'm hoping they'll enjoy communicating with me, but I haven't had any communication with them. I did go to the University of Geneva for particle physics. I took particle physics there, and I did communicate with them. They were pretty nice to me. We talked back and forth, and I said, we focus and we use CMOS. And at that point, they said, no, you really can't do that. And I said, yes, you can. CMOS works. And now they agree with it. It does work. You see, this goes back to 2019. Now, I went to the University of Geneva there. I don't know, it was 2017, I think, 2016. But this is the first use of CMOS. You see it? Development of CMOS for detection of single charge particles. That's what we do, single particles. And then they said this is the first use that they've ever used CMOS for, to detect these particles. Before, they were using charge coupled devices, which they gave it the observer effect, where anytime you look at it, you destroy the whole thing, because you'd be sampling and changing the outcome. All right, when I first went to University of Geneva and I told them what we were doing, they said, no, that's impossible. And I said, no, CMOS can detect these things. Now, this just came out in 2019, because we were doing it. All the things I'm going to be showing you happened in 2015. So they did finally say, yes, you're right, development of CMOS apps for detection of single charge particles. This was the first use of CMOS to detect these things. So they're now into this. They understand you can do this with the CMOS image sensors. You can actually see these single particles. All right, I'm going to try to go through this quickly, because it's not that difficult. Well, let me pump it up. This is what they think happens when they take they can see these particles come out. They take a proton and a neutron, bam, or two protons, bam, and they go all this stuff. Well, we started with light, so we didn't have to dig through all this stuff, because what they get is just a gigantic pile of debris. This is what they see. It's worthless. You can't really make anything out. What we see when we crash our light particles is this. Accelerates the light wave. That's light. So we're nothing like this. We're down in the light, which is light comes right out of these particles, and is this tiny. So we're on zip. So we don't have to look at big, huge particles and dig through debris. This is a particle here. There's a black and a white. And here's what it looks like really up close. In CERN, Fermilab, all of them, they see the same particles, a black and white. It's called a Dirac neutrino. They're attached together. Well, here they are because they're a photon. They never saw this. They've never seen that. We've only seen it because we're just working with light. They see these, but they only see them like here, like I just showed you. They see them in a gigantic collision, and they come out in bits and pieces here and there. But other than that, they have all kind of scraps. Like X means a whole batch of these, and all of these are just little bitsies and onesies, which we see them too after we split up the photon. But that's what we started with, so we don't have all this debris. They really, at this point, are pretty much lost as far as what particles do, because this is what they see. All right, so now let's get past that. What really everything is made out of is that particle right there, a black and a white, a black and a white. All right, this is called a Dirac neutrino. This is the Majorna neutrino, which is in the phase between. Sometimes they're not completely black on one side and white on the other side. They're sort of half and half. That's what's called a neutrino phase, and that's what they're seeing. When we accelerated the light, right here, the particle's inside the wave. The wave is a magnetic field that surrounds the particle, and the wave has to push all the other things out of its way. See, they're finding all kinds of things now that they never realized were out there. Now, the particle just pulls itself right out of the wave because it has to accelerate, and then it splits and creates fission and fusion and electron showers. That means stunning amounts of energy. Electron showers are the cat's meow when it comes to energy. We started with this. There's no energy there to speak of at all. And then it went into this, which is energy on steroids because of the Venturi. And then at the Venturi, we could actually see the particles separate right here. That's what it is, and here they are separating right at the Venturi. This is the whole nut in one shot. Acceleration, division, particle. That's what they see at CERN, but they see them in bits and pieces here and there. They don't know they were attached together, making photons like this. But we can see it, and again, I think I showed you this, maybe I didn't. They are, oh boy. Let me just pick it up here. They're trying to figure out what all these particles are in, and the sun, what does it give off, and where's the energy, where's the plasma, where's the weak force, electromagnetic. They're just totally lost at this point. It's saying under the electroweak theory, neutrinos could interact with photons. Well, guess what? The neutrino makes the photons. So right there it tells you they're lost. The researchers found that that's the case. If a star's atmosphere could produce a right kind of environment for the electroweak Hall effect, the interactions could be taking place there. Well, it's the scrub, and I'll explain it to you in a second. What they don't understand is the state of energies in everywhere. They're talking about in the paper, this guy calculate the energy states of the system of the photon and neutrino during this interaction. They are the same particle, so I don't know what he's calculating. In addition to its contribution to our understanding of fundamental physics, which is the most fundamental particle there is, our work might also explain something called the solar corona heating puzzle. The outside corona of the sun, which is thousands and thousands of miles away from the surface, is millions of degrees. The surface of the sun is only 10,000 degrees. How could it get to be 10 million out there way out here, and it's 10,000 down here? It doesn't make any sense. The only reason is because way out here is where the atmosphere stops, and that's glued to the planet basically. And as it scrubs through the universe, that's where the scrubbing takes place. Just like spinning your tires on a road, that's where the heat takes place. This is what happens. These things scrub through the universe. We have the same problem here on Earth. Right here, it's only 100 degrees on the surface, let's say. Then it goes down to minus 60, and then it goes back up to as much as 3,600 degrees out here. Why? Why? It's because our atmosphere is scrubbing too, and we are blowing up our atmosphere like a balloon now, and it's scrubbing so hard. The heat out there is just unbelievable, and every day it's a turmoil on Earth because it's never shrinking. We're just expanding, and it's scrubbing harder and harder and harder, and that gives you more and more turmoil in the upper atmosphere, and that's what creates the rainstorms and all the heat and the violent hurricanes and all that stuff. It's because of the scrub. We just don't understand the scrub. Everything scrubs as it spins. There's nothing, and everything that's got an atmosphere glued to it spins like crazy and scrubs like crazy and gets hot like crazy. All right, so it's all about the scrub of the particles, and they don't realize that they don't realize space is filled with particles. I'm not kidding you. It's absolutely incredible. They don't realize. They think space is a vacuum. There's nothing out there. It's saturated. Light is a particle. This is what light is. Light is a particle. That's what light is. Where do they think how the light gets here? There's just nothing in between. It's all these particles. And they create zillions of magnetic fields. That's why light's slowing down. It's not the universe is expanding the way they say. The only reason they say the universe is expanding is because as the light goes, it's supposed to stay this speed, because that's what Einstein says. Never supposed to go faster or slower. No, it can go faster or slower, which means it stretches, or it can go faster, which means it's getting into the blue range. The stretched range is the redshift. They say if it's shifting, that means everything has to be moving away because the light never changes speed. No, light can go fast, it can go slow. I can prove that right here. It's very, very simple to show. Here's the blue coming through fast, coming out slow. When it comes off the sun, it's coming out like a rocket ship, and as it goes through space, it slows down. And eventually it turns into cosmic microwave background because it's so slow it hardly moves. And this is the neutrino phase, this is the photon phase, and this is the explosion phase where it turns into the two different particles, the black and the white, separate. So that's a neutrino, these are neutrinos, and that's the photon. All of this is very, very easily understood now if they just stop and take a look at this particular research. All right, light coming through here. There's the black right there. The black pushes the white. The white is just fluff, and it's magnetically bouncing out. The black has no magnet bounce at all. It just pushes. The black is a carrier, and I always said that. I don't know why they change their minds all the time. Black is the carrier boson. The white is the powerful boson. The other one is the carrier. This one has all the power. That one has just the carries it. So they're coming around. They're starting to understand a little bit. But the only two particles that exist are these two, the white one and the black one. That's it. Everything else is made out of those two. A gluon is those two. A photon is two gluons, back to back, just like two-bar magnets. All right, so here's the, where is it? Right there, that's what the photon is. Now, that's a stable particle. It's got two back to back. If you had only one of these, it would be considered an electron. You know what electricity does? It goes into something. Well, light just bounces off because it's just like it's just got a big bubble of magnetism around it. So light is a totally different story. It's the smallest stable particle there is. Once you get below that, and you have just a white or just a black or just one of these, and then it's not stable whatsoever. It's instantaneously going to do something. It's going to adhere to something, or it's going to burn, or I don't know what, but it's not going to stay individual like that. It's got to get to at least that, and then they start to build molecules after that, and eventually you get up to something like this, which is a proton. It's 1,830 or 1,823 particles. It's not just one. They say a proton is one like that. No, absolutely not. When they smash them together, they see all kinds of bits and pieces. But when they're nice and stable, they're all one big ball. But once you start to get down into the guts of this ball, that's when you find the particles that I'm showing. All right, this is the ball. When they smash, boom, they go all over. But this is really the balls. These two hit like this, and then all these bits and pieces go. That's all you're looking at. All right, so hopefully you understand. I'm trying to work with CERN right now, and I've got some connections going on, but I don't know. They're pretty hard-headed. Let's see what they have to say. But I've gone through this, and believe me, you're not going to get anything out of this. They're just talking about this and that. But here's the deal. I'm going to wrap it up right here. This is what they don't understand and do understand. They know molecules are made out of all kinds of little bits and pieces called protons and neutrons, and that's all that exists to them is protons and neutrons. They make up molecules, huge things. Atoms have a central nuclei, which is that, and then they have a few particles spinning around, which are the electrons. They strip off the electrons, and they say they can strip off the electrons, which is only a few electrons in carbon, and end up just with the nuclei, which is a heavy nucleus now. And then they can see the nucleons and quarks all come out of that. Well, that's just all basically completely wrong. If they strip off a few electrons, all right, they can get down to a smaller carbon. Yes, carbon has all kinds of sizes. You know how many pieces, different pieces of matter they call carbon? It's absolutely, and they're all the same way. Every one of these has dozens and dozens and hundreds and sometimes thousands of what they call isotopes, which means it's not just carbon. It's carbon plus 1 or plus 2 or plus 3 or plus 4 or plus 20 or carbon minus 10 or minus 20 or minus 30. There's just all kinds of carbons. They say there's only 6 electrons. No. There's as many electrons as there is of the black particles. It's the same number of glowy ones as there is the black ones. This is just totally wrong. Complete and total wrongness. You see this? They say an carbon has only 6 electrons. You see carbon here? 6 protons, 6 electrons. Well, protons are 1,823 of these particles. Electrons only 1. So they got 6, they say. No. They got a bazillion of them. And they strip the 6 off and they say, now we got a heavy ion. Well, look at this. These are all carbons. Carbon, 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 carbon. Well, what's the difference between all these carbons? They get the same name. It's all carbon. The mass is the difference because some of them don't have enough. See, 8, 9, 10, 11, 12. Now they're getting up to stability. 12 and 13, you're in a stable. Then they go up past that, 14, 15, 16, 17. These are just more particles adding together. And they're still, and these are the half-lives. But they're still carbon, 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 carbon. They take 6 away. That's not enough. All you did was all they're doing is working with particles. Some particles, if you have a few more, a few less. That's what an isotope is. They took 6 of these off and then smashed them to bits and thought they were really doing something with heavy ions to find these neutrinos. And no, they're not. The neutrinos are there all along. Taking 6 away means nothing. All right, I'm just going to leave it at this. It gets very frustrating because it's hard to explain this, and people don't have the ability to understand. They really don't. We're coming through here with light. That's light, light, light. It's not big protons. Protons are 1,800 times bigger. We got a muon neutrino and electron neutrino. That's the black and the white. The white goes into showers. The black stays just that little black ball. The only reason we can see that, because it's dark matter, is because it's sitting on top of the white, obstructing the white from coming through. That never happens in nature. It never does this. The only way you can do this is in a nuclear bomb, which they do, are these nuclear explosions and head-on collisions. They can see them, but they really don't understand them. We saw them attached together and then splitting apart, which is the neutrino phases going into the muon electron shower. That's supposed to create literally a couple of hundred at least times the input energy. So if we can get a couple of hundred energy increase to here, I mean, that's free energy, and that's what we're looking for. That's what the whole idea of all these experiments is to see these particles. We're seeing them. Now, I know it's going to disrupt some people's lives, but that's just the way nature is. These are the particles right here. Green, blue, red, they're all the same particle. You just saw the green ones. Here's the red ones. And here they are turned from neutrinos into photons. It's just as simple as that. The more energy they stack up on themselves, a photon is nothing more than a particle that will bounce back at you. When they're in neutrino phase, they're not really doing much. They're just going through the air. But once they hit something and bounce back, what you're seeing is the bounce. And that's why I hold this thing up and I say, why are all these colors here? How come they're all different colors? I have the same light is hitting this. Why does that one come in this color and these are blue and these are yellow and all that? It's because of the the material that these colors are made of have a different bounce. One of them's like a pillow and it bounces off in red. One of them's like a shard of glass and it bounces off in blue. The harder it is, the harder to bounce. The harder the bounce, the faster the particle. The faster the particle, the more towards the blue. It's not that all hard to understand. But they've never seen these particles before. Because they're working with this giant stuff, all they see is a big pile of stuff. That's it right there. And we don't see anything like that. We see this right here. Right there. Well, let's do it. This shows you all at once. There's the particle of light. There it is exploding. There it is dividing. There it is coming back together. Those are electron showers and muons. Exactly like they say at Fermilab and CERN and all the rest. And I think I told you, but I did go to University of Geneva I didn't go there, but I took an online course at particle physics. I interacted with them. They were very nice. And they looked at my stuff, and at first they were, oh, no. I said, but by the time I was done, I think they were convinced. Because they're doing exactly the same thing we did now. They upgraded, put in focusing magnets and CMOS. The first time it's ever been done in these big colliders, because they had to harden the CMOS. It wasn't as easy as doing what we did, because we're just looking at little light particles. When they hit those big things, they can damage these cells because they're shooting off huge particles. We got one particle we're working with. All right, so we can't damage the CMOS. They're throwing off particles like this, and that hits the CMOS. Well, it's a whole different story. But now they've done something to harden the CMOS so it won't destroy it. Because that's what their original fight was. Oh, no, you're going to destroy CMOS. You can't do that. I said, no, we're using with the photons. You guys are using protons. And eventually it worked out. Anyway, I love you all. I'll talk to you soon. See if we can get this, to get free energy would be pretty nice. And I don't see where it's impossible. I don't see at all that it's impossible. As a matter of fact, I see it as a very likely possibility. Okay, let's just leave it at this. This is the electron flood theory, dipole electron flood theory. Now, you saw the particles, there they are. That's what the photon really is. Half of the photon is the gluon, and there's an electron and a muon neutrinos. Now, this may not be right. I've come to the conclusion it's more likely that there's nothing but electrons surrounding nothing but a dark core. I thought at first maybe there was the dark core and then the really tight ones and then another dark and then another color and then another dark and then a red on the outside. I don't think so. I think now this is actually what the atom is. All the dark goes to the center, and then the other ones are just stacked up against themselves, and the blue is pushed in so tight against the center that when you take blue out of there, you got a rocket ship. And when I liberate blue with a blue laser into a light-emitting diode backwards, I put the light in instead of the light coming out. I can produce 2.44 volts using blue. I can't get anything using these colors. They just don't have enough energy. The red and the green does nothing. You have put the blue on that LED. An LED emits light when you put electricity in. Everybody, I think, knows that. You turn the electricity on, the LED sends out the light. Well, if you put light into the LED, it's going to send electricity out. But you have to have strong enough light, and the only one that's strong enough is the blue. So that's my new model of the atom. And it's not just one big solid core and a couple of little electrons. No, there's as many electrons as there is dark parts. That's how it works. So electrons no longer have that little minute space. They are equal to the dark particles. And of course, this would be all covered up with the colored ones. And anytime you bounce into there, that's all you're going to see is color coming back. You're never going to see the dark matter. The only reason you saw it is because it sat on top of the white matter. If it didn't sit on top, you'd never see it. You see? There it is right there. It's on top of the white. We can't see the white. That's never going to happen in nature. You're not going to ever see that. because they're so tightly glued together. The only way we forced them apart was that tiny, tiny little restriction there. It won't let the black through. All right, that's enough. I love you all. Hopefully we get some something out of this. That's what I'm hoping for. Thank you.